Have you ever wondered how your favorite app can search through literally millions of items and find what you want in like a split second? Well, today we're going to pull back the curtain on the secret sauce that makes it all possible, the B-Tree Index.
I mean, really think about it for a second. You search for a song, you look up a friend's profile, you're trying to find a product, and bam, it's just there, instantly. Now, this isn't magic. It's a really, really brilliant piece of computer science that's all about organizing data in an incredibly clever way.
So, yeah, how do databases manage to find that one tiny needle in a colossal digital haystack so fast? That is the exact question we're going to dig into right now.
Okay, so to really appreciate just how clever B-trees are, we first have to understand the problem they were designed to solve. And it all starts with how data is physically actually stored on a disk.
So, imagine your data is stored in these little boxes called blocks. A disk can only read one full block at a time. Let's just use some simple numbers here. If a block is 512 bytes and one row of your data is 128 bytes, well, you can only fit 4 rows in a single block. So to store just 100 rows, you'd need 25 of these separate blocks. You can see how this starts to add up. Now, if you need to find one specific piece of data, the database has to do what's called a full table scan. And it's exactly what it sounds like. It has to open block 1, check it. Open block 2, check it. All the way up to block 25. For a big table, this is just painfully slow.
Yeah, opening every single box in the warehouse is not a great strategy. So developers came up with a much needed shortcut, the index.
You can think of it exactly like the index at the back of a textbook. You wouldn't flip through every single page to find the topic, right? Of course not. You look it up in the index, get the page number, and go right there. A database index is the same idea. It's a separate, smaller list that has just 2 things: the piece of data you're looking for and a pointer that says, hey, the full record is over here. And the difference is just staggering. Instead of slogging through that huge data table, the database just quickly scans the much smaller index first. Once it finds what it's looking for there, it uses that pointer to make one final, direct jump to the data block it needs. The number of disk reads just plummets.
So we've gone from a potential 25 reads all the way down to just 5. That is a massive improvement. But this solution has a kind of hidden flaw. What happens when our data grows from 100 rows to, say, 1,000,000?
Yep, our nice, simple fix has a scaling problem. As our database gets bigger and bigger, that helpful little index, well, it stops being so little.
And that is the absolute key question. If our database has 1,000,000 rows of data, our index is now going to have 1,000,000 entries. We've just recreated the original problem. We're back to searching through a gigantic list. Sure, it's an index list, but it's still huge. There's got to be a better way.
And there is. The solution is to change our way of thinking. We need to stop thinking about the index as one long, flat list and start thinking about it as a tree.
This is where things get really cool. The brilliant idea is to build an index of the index. Stay with me. We create a small top-level index that doesn't point to the data. Instead, it points to different sections of our main index below it. This creates layers, a hierarchy, and what you end up with is a tree-like structure.
And just look at the performance boost. For a table with 1,000 rows, we're down to just 4 block reads. Instead of searching a long list, we just make a few quick hops. We read the top node, it tells us which branch to go down, we follow it to the next level, and boom, we land right on the data we need. This is getting seriously fast now. So this tree-like structure, this whole concept, is the core idea behind what is probably one of the most important data structures in the entire world of databases. It's time to officially meet the B-tree.
A B-tree basically perfects this multi-level index idea. And its superpower, the thing that makes it so incredible, is that it is self-balancing. This is huge. As you add or delete data, the tree automatically rearranges itself. A node gets too full, it splits. Nodes get too empty, they merge. This makes sure the tree always stays short and wide, which guarantees that finding anything is always just a few hops away.
Now, in the real world, you'll usually see a popular variation called the B-plus tree. The main difference is that in a B-plus tree, the actual pointers to the data are only stored at the very bottom level, in what are called the leaf nodes. And crucially, all those leaf nodes are linked together, like a chain. This makes range queries, like find all sales from last week, unbelievably fast, because the database can just zip right across that bottom-level chain.
So the whole process is just beautifully efficient. Let's say you want to find key 302. You start at the very top, at the root node. It points you down the right path to an internal node. That node then points you directly to the leaf at the bottom, which finally has the pointer to your data. A journey through millions, maybe billions of records is cut down to just 3 or 4 quick steps. It's incredible.
Okay, so this lightning-fast search speed is amazing. But, as with everything in engineering, there's no such thing as a free lunch. This incredible performance comes with a trade-off.
So here's the deal. On the one hand, the pro is obvious. You get these dramatically faster reads and searches. It's fantastic for systems that do a lot of lookups. But on the other hand, the con is that every time you write new data or update it or delete it, the database has to do 2 things: write the data itself and update the B-tree structure to keep it all perfectly balanced. That makes writes a little bit slower. Oh, and of course, the index itself takes up extra space on the disk.
So the really crucial point here is that this is not an automatic just do it kind of choice. Engineers have to really think about how their application is going to be used. Is it like a social media feed that gets read constantly but not written to all that often? An index is a fantastic idea. Or is it a logging system that just writes new data all day long? Then maybe an index isn't the best choice.
And that really leaves us with the fundamental question that every single database designer has to answer for themselves. For the specific world your application lives in, when is the huge benefit of an instant read worth the small cost of a slightly slower write? The answer to that question is really what separates a good database design from a truly great one.